In this video, we will focus on products of polynomials. This will be done in lesson 1. In lesson 2, the focus will be on special products. And finally, in lesson 3, we will deal with factorization. In lesson 1 of this video, we will consider important aspects of products of polynomials as it applies to the CAPS document for mathematics. To start off, let's have a look at the outcomes for this lesson. In this lesson, we will first of all revise the product of two monomials. Recall that a monomial is a polynomial which consists of one single term. Secondly, we'll revise the distributive law which links addition and multiplication of expressions together. Thirdly, we'll investigate the product between two binomials. That is, where we have two terms. A polynomial with two terms is called a binomial. And finally, we'll investigate the product of a binomial and a trinomial. That is, a polynomial which has three terms. Let us consider the products of monomials. In order to find such products, you should know how to determine the sign of the resultant product. That is, when we multiply two negatives or two positives together, the answer is positive, and multiplying two opposite signs together, the answer will be a negative. You also need to know the numerical coefficient of the product, that is, the multiplicative constant as a factor of such a product. And also, you need to know the product of exponential forms. So you need to know how to apply the exponential rules when two exponent forms are multiplied together. Let us have a look at a few basic examples of this type of product. First of all, we start with a simple example of two exponent forms, a to the power 2 and a to the power 3, multiplied together. Note that this is a single term, so it's a monomial. This is also a single term, a monomial, multiplied together. Since the bases, a, are the same, we are allowed to add the exponents according to the exponent rule for the multiplication of exponents forms. And in this case, we get the result as a to the power 5. This is then the product of the two monomials. The second example, we see we have an expression a to the power 3, b to the power 4 as a single monomial in brackets, multiplied by a similar expression on the right, b to the power 5, a to the power 4. Now in this case, we have to multiply the components or the factors of these monomials where the bases are the same together. So we first multiply a to the power 3 with a to the power 4, and then we get a to the power 7, adding the exponents. That forms part of the product. And we also multiply the factors where the bases are the same, namely b in this case, together to get b to the power 9, which is the second factor then of the product of these two monomials. In example 3, we have a similar situation, although in this case we use the multiplication sign between the two monomials as indicated on the screen, and we start by multiplying the two numerical coefficients together, namely 2 and 3, and we get the product is 6. That becomes then the numerical coefficient of the product of the two monomials. As before, we multiply the expressions in x together, same basis, and we have x to the power 7, which is 3 plus 4, and also the expressions with the base y together, y to the power 5 plus 3 is 8, and thus we generate the product of these two monomials in the same way. In example number 4, we have a similar case where we have brackets representing the monomials which have to be multiplied. In this case, we use the notation a dot. So can you see? We have three different notations. Either just the brackets indicate multiplication, or the multiplication sign, or we can use the little dot with the brackets to indicate that these two monomials needs to be multiplied together. In this case, we start by looking at the signs in front of the numerical coefficients of the respective monomials. A minus times a minus gives us a plus, and that then forms the sign of the product of the monomials. Again, multiplying the numerical coefficients together, we get 6. And in this case, we have m to the power 3. There is no factor in this case with the basis m represented, so it stays the same, m to the power 3. N to the power 4 gets multiplied by n to the power 5, the same basis, and we get n to the power 9 as a result in the product. And again, p on this side is not counter represented by an exponent form with a base p on this side, and we just allow it to remain the same as part of the product, in this case p to the power 4. Let's have a look at another example, example number 5. Here we have a monomial where the numeric coefficient is 9 divided by 4. And we have another monomial where the numeric coefficient is 2 divided by 3. And in this case we multiply the numeric coefficients together first of all. So if you multiply 9 over 4 with 2 over 3, clearly we multiply above the line, it's 18, below the line is 12, and simplify. And then we get 3 over 2 as the numeric coefficient of the product of these two monomials. The rest of it is exactly as we saw before, multiplying the components or the factors of the monomials with the same basis together. X to the power 2 times x to the power 1 gives us x to the power 3, and the same y to the power 4 multiplied by y to the power 3 gives us y to the power 7. And hence we have generated now the product of these two monomials in the same way. Finally, we look at example number 6, where we have a similar situation as before, but now we have exponent forms below the line. How do we handle that? Here we need to think of our exponential or exponent rules, which deals with the quotient of two exponent forms. So let's just start by multiplying the numeric coefficients together. That's minus 5 over 2 is the numeric coefficient of the first monomial on the left, and you multiply that with the numeric coefficient 4 over 5 of the second monomial on the right hand side. Again, multiplying above the line, minus 5 times 4 gives us minus 20, and below the line 2 times 15 gives us 30. So minus 20 divided by 30, if you simplify, you get in this case the numeric coefficient of the product to be minus 2 over 3. Let's see how we deal with the other components of this particular product of monomials. Look at the expression a to the power 2. We multiply that with a to the power 3, and clearly we get a to the power 5 as before. You can only multiply exponents forms with the same basis together, adding the exponents according to the rule. Now we have x to the power 3 above the line in the one monomial. On the right hand side we have x below the line, so it's x to the power 1. So it's the same as if we have x to the power 3 divided by x to the power 1. In such a case, clearly we have to subtract the exponents, and we have x to the power 2 as the result above the line in a numerator position for the product of the two monomials. Let's consider the y component. In this case, y to the power 3 is below the line on the left, and y to the power 2 is above the line in a numerator position on the right hand side for this particular product. So it's the same as taking y to the power 2 divided by y to the power 3. Subtracting 3 from 2, we have y to the power minus 1. If we represent that with a positive exponent, it becomes y to the power plus 1 below the line. And if this is the way you prefer to write it, our final expression for the product of the two monomials will then be minus 2 over 3 a to the power 5 x to the power 2 divided by y to the power 1. So that then concludes a few examples or demonstrations of how to multiply two monomials together to form a product. This brings us to the first tutorial of this video, where you will get the opportunity to practice products of monomials. I would like you to write down the following products. We have four problems here, 4 cases where we have to multiply monomials together into a single product. And just take note with number 3, this particular numerical coefficient must first be written as a proper fraction, okay, and then you can try to apply the techniques that we have seen in the previous examples to complete this particular exercise where you multiply together these monomials. At this point in time, I suggest that you pause the video, do tutorial 1 and then come back and view the solutions. Let us have a look at the suggested solutions for tutorial 1. In the first case, we have to multiply these two monomials together, and clearly a negative times a negative gives us a positive result for the product, and x to the power 3 times x to the power 6 gives x to the power 9, adding the exponents, and y to the power 4 times y to the power 5 gives us y to the power 9, again adding the exponents. So you should all be able to do this one. Is that right? Let's have a look at the second case. Again, we have two brackets here, multiplied together, representing monomials each of them, and multiplication of two negatives gives us a positive. 2 times 3 is 6, and again a to the power 3 times a to the power 1 gives us a to the power 4, and similarly b to the power 1, which is just b, multiplied by b to the power 4 gives us b to the power 5. I hope you got that one as well. In the third problem, we have to multiply together again two monomials, but in this case we have to first replace this particular improper fraction with a proper fraction. So we have 9 over 9, add to that 7 over 9, it gives us 16 over 9. Now we're ready to multiply the two monomials together as before. Again, multiplying above the numerical coefficients and below, and then simplifying, we have the answer of 4 over 3. Check that you got that correctly. And again, multiplying the exponent forms, x to the power 2 with x to the power 3 gives us x to the power 5, and similarly y to the power 3 or y cubed multiplied by y to the power 5 gives us y to the power 8, adding exponents according to the rules. Finally, question number 4, we have to multiply together again two monomials where we have above and below the line expressions in the unknowns, in this case a, b and c. We start off by multiplying the numerical coefficients together, minus 3 over 2 that is, multiplied by 8 over 9. Negative times a positive gives us a negative, so the sign is the first thing that you have to look for. And then multiplying the numerical coefficients together, 3 times 8 divided by 2 times 9 gives us finally, after simplification, the numerical coefficient 4 over 3. Now we have to be careful. Look at the exponent form a to the power 2. There is no a to the power anything as part of the second monomial on the right hand side, so it just remains a to the power 2 as part of the product in this case. In the case of the exponent form b to the power 4, that must be divided by b to the power 2 and applying the exponent rule. In such a case, we have b to the power 2, that is b to the power 4 minus 2, subtracting the exponents. And similarly, if we look at the exponent form c to the power 2 on the right hand side and c cubed below the line on the left hand side, it is as if we divide c to the power 2 divided by c to the power 3, and then we get the result according to the exponent rule c to the power minus 1, which if you would like to write it below the line becomes c to the power plus 1, and that gives us the expression that we see on the screen. So hopefully you also have this one correct. Let us consider the distributive law for algebra. This distributive law, which is very important, allows us to convert other types of products of polynomials into the sum of products between two monomials of the type that we saw before. Let's try to explain what this distributive law is all about by using this particular diagram. We have here a rectangle consisting of two smaller rectangles, a yellow and a green one, with dimensions as indicated, width a and length b plus c. Now if we consider this particular expression, clearly it represents the area of this rectangle as a whole, where the dimensions are a and b plus c, as mentioned before. So if we consider, for example, this particular expression, a times b plus c, it's the area of this big rectangle. Clearly it's the sum of the areas of the two smaller rectangles, that is the yellow and the green one respectively. But these areas can be represented by AB and AC respectively. So we see that this particular expression on both sides of the equation represent the area of the big rectangle. Or we could have actually multiplied the distance B plus C, or the length B plus C, with A in this order, and clearly also get the sum of the two products, which represents exactly the same area in total. So we have from this that all these expressions really represents exactly the same, namely the area of the big rectangle that we started out with. So it must be the same. Clearly we assume here that A, B and C represent positive real numbers. Let's generalize this. This is exactly what we can also see as what the distributive law does. Multiplying from the left, that is any real number A, with the sum of two real numbers B and C as indicated in the brackets, we have that we might as well represent that same expression as the sum of two real numbers, namely A times B and A plus C as indicated on the screen. In fact, since we have the commutative rule for algebra as far as multiplication goes, in other words, A times B is equal to B times A for any two real numbers A and B, we might as well start with the bracket, and within the bracket the sum of the two real numbers B plus C, and then multiply a real number from the right hand side. And in the same way we can represent this particular expression as the sum of two products, namely BA plus CA as indicated on the screen. And by the same commutative rule, since we may swap any one of these two factors around with the two terms as indicated, we see that this is also equal to the expression AB plus AC. So this is known as the left distributive rule, where we multiply from the left into a bracket which contains more than one term, and this is called the right distributive law, and the way we actually multiply out is clear from these particular expressions, which has exactly the same value in the end. Let us have a look at a few examples where we apply the distributive law. In the first example, we have to multiply the monomial minus 2a squared b to the power 3 into the bracket which contains three different terms. Each of these terms represent a separate monomial. So as we saw from our distributive law, this particular monomial must be multiplied with each one of them independently. So we immediately have this particular expression. Our monomial in front of this bracket initially multiplied with the first term 4a squared, and then in this case plus, and we take the monomial in front, which is minus 2a squared b cubed, multiply with the second term. Note the second term is negative, so we use our brackets here to keep track of the negative signs. It is not minus 3ab, it's multiplied with minus 3ab if you put the brackets, plus, and then we multiply our monomial in front again with the third term, which is minus b squared. Make sure that you actually apply the brackets in the correct way as indicated in this particular expansion. We say that we expand this particular bracket by multiplying in and writing it as a sum of terms as indicated. Now it becomes exactly the same as what we had before, multiplying two monomials together, but you have to do this in all three cases for the three terms as indicated. So the next step would be to multiply these monomials together as before. Minus times a plus is a minus, 2 times 4 is 8, and you multiply the exponent forms with the same basis, a together, get a to the power 4 and b to the power 3 alone as we had it before. And in the second product, to determine the second term of this expansion, we have minus times a minus is a plus, 2 times 3 is 6, a to the power 2 multiplied by a to the power 1 is a to the power 3, and b to the power 3 times b to the power 1 is b to the power 4. And you should all be able to see that if you multiply these monomials together, we get plus 2a squared b to the power 5. Now that's a good example of how the distributive law applies in this case to expand a bracket in the way that it's indicated on the screen. Second example. Here we have the monomial on the left hand side in front of the bracket as minus 1 divided by 4a squared b to the power 3. So as before, this particular expression must be multiplied with each one of the terms. There are 3 terms in the bracket in this case, according to the distributive law, and that must then be multiplied individually to find the terms of the final expanded version of this particular product. So let's see how that is done. Again, use your brackets because we have a negative to take care of as part of the multiplication. And we have here the monomial in front multiplied by the first term plus the same monomial, use your brackets, multiplied by the second term, indicate again, use the brackets because we have a negative second term in the brackets there, and we again multiply plus the product of minus 1 over 4a squared b to the power 3, the monomial in front multiplied by the third term in this case. Now, as before, we multiply through. This is really 12a to the power 4 b to the power 3 divided by 4a squared b to the power 3 after we have taken care of the sign of this product. Minus times a plus gives us a minus, and 12 divided by 4 is 3. And again, exponents forms with the same basis. A to the power 4 divided by a to the power 2 gives us a to the power 2. And in this case, the b to the power 3 and the b to the power 3 will cancel above and below if you actually multiply through. Similarly, for the second term, if you multiply out, just check, you get a positive. And we have, in this case, a to the power 1 above the line and b to the power 2 below the line if you use the exponent rules for multiplication and division of exponent forms. We have checked that before. And finally, if you multiply the third term out, we have again a negative because the minus times the plus. 8 divided by 4 is 2, and in this case we see that a to the power 2 b to the power 3 below the line and a to the power 2 b to the power 3 above the line will in fact cancel if you apply the exponent rules, and we have minus 2 for the third term of this expansion. Note that the product that we started out with can also be viewed alternatively as the expression in the bracket divided by minus 4a squared b to the power 3. So instead of multiplying by minus 1 divided by this particular expression 4a squared b to the power 3, we can view this as the expression in brackets divided by this particular expression. In some cases, this is also handy to see it this way because it really means that we take this expression and we divide it into each one of the terms of the numerator of such an expression. In tutorial 2 of this video, you will have the opportunity to try a number of problems where the distributive law of algebra will be applied. Let's have a look at these problems. Use the distributive law to find the following products. In all cases, you have to multiply from the left by a monomial of some kind that we have seen before into a bracket which contains, in most cases, more than one term. Note also in problem number 6 that dividing by minus 8a squared b cubed is the same as multiplying from the left by 1 divided by this particular denominator expression. At this point in time, I suggest that you pause the video, do tutorial 2, and then come back and view possible solutions. Let us briefly have a look at the suggested solutions to tutorial 2. In the first problem, we had to multiply the monomial AB from the left into the bracket as indicated. Applying the distributive law, we multiply AB with each one of the terms inside of the bracket, and thus we get 3a squared b minus 5ab squared and minus 6abc as the result. Check and see that you have the same terms if you expand this particular bracket. Note that not one of these two terms contain exactly the same factors in the bases a and b, so this particular expression cannot be simplified any further. In the second problem, we have a similar situation, except that we have a numeric coefficient 3 over 2 in front to deal with. So you can see that if you multiply 3 over 2 with 4, minus 6 and 2 respectively, we have the numeric coefficients of the three terms in the expansion if we apply the distributive law in such a case. Also check that if you multiply AB with each one of those particular terms, that you have the expressions a to the power 4, b to the power 2 in the first case, a to the power 3, b to the power 3 in the second case, and ab in the third term. That is, if you apply the exponent laws in each case for the bases a and b respectively. Problem 3, we had to multiply 12xy into the bracket with the two terms x over 4 and minus y over 3 respectively. In this case, we have to first look at the numeric coefficients. If you multiply 12xy into the first term in the bracket, we might as well divide it by 4, 12 divided by 4 first of all, and then of course x times x is x squared, so you have the resultant term 3x squared y. And similarly, if you multiply 12xy with minus y over 3, we first divide the 12 by 3 to get the numeric coefficient 4. Remember, there's a negative as well. Plus times a negative gives us a negative. And we also multiply the xy with the y to get xy squared in this case. In the fourth problem, we have a similar situation, except that inside the bracket we have now one algebraic fraction, and in the numerator position two terms like this. So as before, we first consider the denominator 2c and the factor 4cd. So it's like 4cd divided by 2c, and in such a case we have 2d. Now this 2d then gets to be the monomial to be multiplied into the bracket with the numerators 4a minus 3b, as you can see on the screen. Multiplying out in this case, we get 8ad in the first instance if you apply the distributive law, and in the second case we get minus 6b times d, or d times b. Remember, the commutative law applies, so the order in which these factors appear with each of these terms in fact is not important at all. Finally, in problem number 5, we have a similar situation where we have to multiply the monomial 1 divided by 3ab into the bracket where there's three terms, as can be seen. So doing it individually, applying the distributive law from left to right, we first look at the numeric coefficient for the first product, which is minus 6 over 3, gives us minus 2, and then we look at the 1 over ab multiplied with a to the power 3b squared, or you can view it as a to the power 3b squared divided by ab. In this case, applying your exponent law for the quotient, in this case we have the resultant expression a squared b for the first term of such an expansion. Multiplying 1 over 3ab with 3ab, clearly there is cancellation and we're left with the number 1. Remember, that is still a number that represents a term. It is not 0. Everything doesn't cancel. You have to add plus 1 in this case, and multiplying the particular expression 1 over 3ab with minus 9 in this case gives us finally 3 divided by ab in the final instance. In fact, we have problem number 6 as well, and in this case we have a quotient where there are, in this case, three terms in the numerator position. If you divide each one of those terms independently by minus 8a squared b cubed, it is the same as multiplying 1 over minus 8a squared b to the power 3 into the bracket which contains the terms in the numerator position, as we saw before. So, multiplying or dividing minus 8a squared b to the power 3 into the first term, we have in this case minus 2a squared b squared. Check that. If you divide minus 4a squared b next with the denominator separately, we have plus 1 divided by 2b squared. And finally, if you take term number 3 in the numerator position and divide it by the expression minus 8a squared b to the power 3, clearly it's the same expression except for the minus 1, and the result then becomes minus 1. So you can see that the distributive law in this case applies. It is as if we have multiplied 1 divided by minus 8a squared b to the power 3 into the bracket containing the 3 terms in the numerator position. So that then concludes the suggested solutions for tutorial 2. In this part of the video, we will consider the product of two binomials. Note that the binomial is just a polynomial consisting of two terms. We have three different methods that you may use to find such products. In the first instance, we may decide to apply the distributive law that we saw before. Let's have a look at the situation. We're asked here to multiply the binomial a plus b, can you see two terms in the blue brackets, with another binomial c minus d, for instance, in the black brackets. So we may decide to see the a plus b binomial as a unit and then apply this distributive law from the left. In other words, multiply the binomial in the blue brackets with the terms in the binomial expression with the black brackets, as can be seen on the screen. That means that a plus b must first be multiplied with c, and then afterwards a plus b as a binomial must be multiplied with minus d, as we can see. And then after that we may decide to view the c as a monomial to be multiplied into the bracket from the right hand side, as can be seen on the screen, and also with the second term in this case view the d as a monomial to be multiplied into the bracket from the right hand side and apply the distributive law as before. If we do that, then c must be multiplied with a and c must be multiplied with b to get ac plus bc. And secondly, if we multiply the d into the blue bracket a plus b with the a plus b expression, then we get the term minus ad and minus bd, as can be seen on the screen. Or you can actually decide to view the binomial represented by the blue bracket here as a unit and multiply using the distributive law from the right into this particular expression, the binomial represented by the black bracket in this case. If we do that, then clearly the unit c minus d as a binomial must be multiplied with a first, and secondly it must be multiplied with b. And then we apply again the distributive law, multiplying the monomial a into c minus d as well as the monomial b into c minus d in this case. And then we have the expression as you can see on the screen by applying the distributive law in that particular case. So that is one way of applying the product of two binomials, by using the distributive law twice in such a case. There is a second method to multiply binomials together by means of so-called inspection. Let's see what that is all about. Here we have the product of the two binomials, and we may first decide to multiply the first terms together. After that, the outer terms, that is the first term on the left with the second term on the right, and thirdly the inner terms, that is the b with the c as indicated on the screen, and finally the last terms for each of the binomials. That's the second term on the left with the second term on the right. That's the so-called FOIL rule for expanding such a product. That's the first terms, outer, inner, and then last terms multiplied together respectively to form the expansion, the four terms as can be seen on the screen. So this is a very useful method of expanding two binomials. There is a third method, that is to use a multiplication grid. Let's see what this is all about. We may want to find the terms for the left hand side factor, the first binomial, and write down the terms a and b as can be seen in a row for this particular grid. And then the second binomial, the term c and minus d, write it vertically to complete the structure of this grid, and then complete the grid by just multiplying the particular terms together as can be seen. And now we can utilize this particular grid by listing the elements of this grid to become the terms of the expansion of such a particular product of binomials. Note that the order in which these terms are to be written is not important at all, and also within each term the order of the factors in this case will not be important, since we have the commutative rule that applies for products. A times B is equal to B times A in all cases. So these then are the methods that you can apply to expand two binomials, the product of two binomials, and I would actually suggest that method 2 should be focused on and practiced in order to make yourself familiar with such expansions of a product of two binomials. Let us look at a number of examples of where we apply the techniques to expand a product of two binomials. In the first example, where we have the two binomials as indicated in the brackets, if we multiply this together and if we decide to use the distributive law, then in the first case we will take the unit 2a plus 5c, that is the binomial on the left hand side, and multiply it into the bracket using the distributive property. So we first multiply it with 5a and after that with minus 3d. And in the second round we take the monomials 5a and minus 3d and multiply it from the right hand side into the binomial expression 2a plus 5c to get the expansion, as we saw before, of the product of the two binomials as indicated on the screen. If we decide in example 2 to multiply these two binomials together using the inspection method, then we get the following expression. Remember, this comes from multiplying the first terms together, 3a and 2a, that gives us 6a squared. After that we multiply the first and the last, okay, the outer terms, so to speak. 3a times minus 5d gives us minus 15ad. After that we multiply together the inner terms, 4d and 2a as indicated on the screen, to get 8ad. And finally we multiply the second or the last terms for each of these binomials, 4d and minus 5d together, to get minus 20d squared. That is, of course, if you use the well-known FOIL rule. Let's have a look at another example, but before we do that, just take note that in this case we have generated, in using the FOIL rule to expand this particular product, two terms which are of the same type. The AD determines the type of the term in this case, and we have 8 of the one and minus 15 of the same type. So that can be consolidated or simplified to give us the final expression for the expansion of the product of these two binomials, namely 6a squared minus 7ad, which is of course 8ad minus 15ad together, and then finally minus 20d squared in this case. In the third and final example, we again have a product of two binomials, and we apply the FOIL rule again. So first terms first of all multiply together, then the outer terms followed by the inner terms multiply together for the product in this particular format, and then finally we multiply the last terms for each of these binomials. And if you do that and apply the exponent rules in each case, consolidating your numerical coefficient for each product, we have the following expression, which of course again generates terms of the same type. The second and the third term in this particular expression are of the same type. We have 12 of the one and minus 35 of the other one, and the type is a squared b, and we consolidate and simplify to finally get the expansion in this case, applying the FOIL rule as 21a to the power 4 minus 23 a squared b, that is 12 minus 35 gives us minus 23, and finally the third and last term here, minus 20b squared. I think you should be ready now to tackle tutorial 3, where we consider a number of problems where each of them represent the product of two binomials. Here we have the problems. And also note that we have indicated the technique that we would like you to use in each case. either the distributive law or maybe the inspection method, even the grid method you can try. In general, we make use also of the FOIL rule as we discussed it before. At this point in time, I suggest that you pause the video, do tutorial 3, and then come back and view the solutions. Let us have a look at the suggested solutions for tutorial 3. In the first problem, we had to multiply two binomials together using the distributive law, and in this case we choose to have the binomial 2c minus AD as a unit to be multiplied across from the right hand side distributively across the binomial in the brackets on the left hand side. So we get 3a times the binomial 2c minus AD plus minus 2b times the same binomial 2c minus AD. The second step would be to take the monomials 3a and minus 2b respectively and multiply it across from the left distributively across the binomial 2c minus AD in both cases. Thus we arrive at the four terms, which is the expansion of the product of the two binomials that we have started out with. Note that all these terms are different, the terms are not similar, and no further simplification is possible. In the second problem, we have a similar product of binomials to be expanded using the inspection method. That really means that we have to multiply each term from each of the binomials with each of the other terms of the binomial, and if we do that, then we get the expansion as we see. The four terms again, all the terms are different terms. Just check if you have the similar expression. Note again that the order of the factors within each term does not matter at all. We normally write the numerical coefficient in front, of course, for each term. The third example or problem in this case, we had to apply the grid method. So we set up a grid and the terms from the binomial on the left hand side form the first row, and the terms from the binomial on the right hand side of this product form the first column. And now we just complete this grid by multiplying each of these terms with the term of the other binomial. So the blue region here represents the different products that one can get, and if we list all these terms in blue, we in fact have the expansion of this particular product of two binomials according to the grid method. Problem number 4, we apply the FOIL rule, which is very similar to the inspection method that we had before, but in a more structured way. So we first of all multiply the first terms together to get 6x to the power 4. After that, we multiply the outer terms together, that is minus 21 x squared y to the power 3, and after that the inner terms, which is minus 10 x squared y to the power 3. And note that these two terms are similar, so we can consolidate. Adding them together we get minus 31 x squared y to the power 3, and finally from the FOIL rule the last terms must be multiplied together, that's the minus 5y cubed and the minus 7y cubed. In this case clearly we have plus, minus times a minus is a plus 35 y to the power 6 according to the exponent rule for multiplication. Example or problem number 5 uses exactly the same strategy, the FOIL rule. In this case we start with for example your first terms gives us 48p squared q squared. The outer and inner terms in this case generate similar terms consolidated. It gives us minus 2pqr, just check that. And finally we multiply the last terms together. Minus 7 times 5 is minus 35, and r times r is r squared. So that should be clear at this point. Finally, we use the FOIL rule as well to solve problem number 6, which is the expansion of the product of two binomials as indicated on the screen. And here is just a normal application of the FOIL rule. Just note that here we have an x in the denominator position for the first term of the first binomial as well as for the first term of the second binomial. So multiplying together, we multiply numerators together and denominators together to get 24 over x squared in this case. Multiplying the first and the last together, we see that there are x's that will cancel above the line and below the line, and 6 times minus 3 gives us minus 18. And if we look at the product of the inner terms in this case, we see that the x's also cancel, and we also have a constant, namely 5 times 4, which is 20. So 20 minus 18 gives us the plus 2, which then forms the so-called middle term of this expansion of the two binomials. And finally, multiplying the last terms together, we have minus 15 times x squared. Now this gives us a very good overview of the exercises linked to products of binomials in particular. Next, we have a very similar situation where we look at the product of a binomial and a trinomial. Now, you guessed correct. A trinomial is just a polynomial with 3 terms instead of 2 in the case of a binomial. So let's look at an example of where we multiply a binomial with a trinomial and where we apply, as before, the distributive property or law to find such an expansion. Here we have a binomial in blue multiplied with a trinomial, 3 terms in a bracket as indicated on the screen. So the distributive law in this case means that we, in this case, take the binomial and we as a unit multiply it with each one of the terms of the trinomial independently. So 2a minus 3b must be multiplied with 5c first of all, then with minus 4a squared b, and then with minus 6b squared c finally. And in this case, each and every one of these binomials on the right hand side, indicated with the black brackets, must then be in turn multiplied from the right hand side using the distributive property across the terms of the binomial as we saw before. And if we do that, we generate in such a case 6 terms, which then represents the expansion of this product of a binomial and a trinomial. Note that no 2 of these 6 terms are in fact similar, so no simplification is possible in this case. Let's have a look at the second method that we saw before as well, where we apply inspection to multiply a binomial and a trinomial. In this case, it really means that we have to multiply each term on the left-hand side, the binomial on the left-hand side. Each term of the binomial must be multiplied with each term of the trinomial on the right-hand side of this product. And if you do that and consolidate the terms using the exponent rules in all cases, just check that, then we have this particular expression as you can see on the screen. But in this case, we have 2 terms indicated in red, which are similar. X squared y to the power 4 is the type of the term in this case. We have 3 of them in the one term and 6 of them in another term. So we add these 2 terms together to get 9 x squared y to the power 4 for the final expression, which is the simplified version of this expansion. Similarly, we have 2 terms indicated in blue, which is also similar but of a different type, namely x to the power 4y squared terms. Minus 9 in the one case and minus 4 in another term. So consolidating, adding them together, we get minus 13x to the power 4 y to the power 2 in this case, y squared. So basically, inspection in this case means that we have to multiply each term on the left-hand side polynomial, which is a binomial in this case, with each term on the right-hand side, okay, the right-hand side being a trinomial, and thus generate the 6 terms as we saw with the first example. In the third example, we may also apply the multiplication grid as before when we multiply a binomial and a trinomial together. So let's have a look at this example of the product of a binomial and a trinomial. In this case, we set up our grid by listing the terms of the left-hand side binomial, 3a and minus 2b is the first row, and the first column the terms of the right-hand side trinomial as can be seen. What we have to do now is to complete the grid by multiplying all possible terms with all other terms to complete this particular grid, and we list all the entries or the terms of this particular grid to represent then the expansion of this particular product of a binomial and a trinomial. Again, we have some terms in this case which are similar, the blue ones again and the red ones, just check that. Consolidating, adding the blue ones together, we get minus 17a squared b. Adding the red ones together in this case, similar terms, we get plus 21a times b squared. And this then gives us an idea of how these three methods then generally extend if we multiply polynomials together in general, whether it's a binomial or a trinomial, whether the one is on the left or the right, it doesn't really matter. We can use any one of these three methods, and with these examples then you should have a good idea of how these products can be expanded. I think you will be able to also cover or tackle tutorial 4 in this case, where we multiply the product of a binomial and a trinomial. So here we have three problems for you to try. In the first instance, you may want to use the distributive law, and in the second case the inspection method, and finally you may also apply the grid method to expand the product in problem number 3. At this point in time, I suggest that you pause the video, do tutorial 4, and then come back and view the solutions. Let us look at the suggested solutions for tutorial 4. In problem 1 we had to apply the distributive law, and let's see how we do that again quickly. We have to take the blue binomial and multiply it with each term of the trinomial on the right hand side of this particular product, and this is what has happened here. And then finally take each of the monomials in the black brackets as indicated and multiply it from the right hand side distributively across the binomial in the blue brackets. So here we go. If we do that, we generate in such a case again 6 terms, and in this case no two terms are similar, so we cannot simplify any further. So check that you have this particular expansion for this particular product. Remember, you can have a different order of the terms, it does not matter, and even within every term or each term the order of the factors does not really matter because of the commutative law for multiplication. In the second problem, we had to, by means of inspection, expand this particular product. What does that mean? Take each term from the binomial on the left, 3a in this case is the first term, and multiply it with each one of the terms of the trinomial on the right hand side of this particular product, and do the same for the second term, multiply it with each of these terms, and then you also get an expression consisting of 6 terms in such a case, and all the terms in this case are also different, so no simplification possible at this stage. Okay, so there we go, multiplying each term on the left with each term on the right. That is basically what inspection means in this case. Finally, in problem 3, we have to use the multiplication grid to multiply together the binomial and the trinomial as indicated, and setting it up in a normal way, 2a cubed minus 3b cubed. That represents the first row, the terms in the first row, and the first column, of course, the terms of the trinomial. Completing the table as we did before, considering similar terms, the red terms are similar, must be added together, and the blue terms as well must be consolidated. We have an expression in this case consisting of 4 different terms as the expansion of this particular product of a binomial and a trinomial. In lesson 2 of this video, we consider the expansion of special products, which will also become important when we discuss factorization in lesson 3. Let us look at the outcomes for lesson 2 of this video. In this lesson, we will investigate the following special products. First of all, the square of a binomial. That is, when a binomial is multiplied with itself. Secondly, we would like to consider a product which will result in what is called a difference between two squares. And in the third instance, we would like to consider products which will result in the sum or the difference between two cubes. Let us consider the first special product, namely the square of a binomial. So it can either be one of these two types, namely a plus b all squared or a minus b all squared. That really means that we have to multiply the binomial in the bracket with itself. And here we have the expansion. Now how do we get to these particular formats? Well, we can decide in this case to use the grid method, as we saw before, listing the terms of the binomial as a either plus or minus b in the first row and a plus or minus b in the first column, and complete the grid. Note that if we complete this grid, that a times a gives us a squared, and whether it's a plus or a minus b, in both cases it will be squared to form plus b squared. For the other terms, the terms in red, that is the similar terms in this case, which will result in the expansion of this type of product, we will either get plus or minus, in both cases, a times b, which can be added together to form the 2ab in the one case or minus 2ab in the other case. So this is then typically how we expand the product known as the square of a binomial. If we look at a few examples of this type of expansion, we see that the formula can be applied in some sense directly from the original product as we have it. In the case of a plus 3 all squared, we know that we have to square the first term to form the first term of the expansion, square the second term, 3 squared is 9, to form the last or the third term of this expansion. And in order to form the middle term, we need to multiply the terms together, and then of course it is repeated twice, as we can see from our grid method of expanding the general form of such a particular product. So we have 2 times 1 times 3, which is 6, and then of course it will be a in this case. 3a times 2 is 6a. And in the case of the negative, clearly we have exactly the same structure, except we have a negative with the middle term in such an expansion. So if there's a negative here, we always have a negative in the middle term of the expansion of the square of a binomial in this case. Second example, very similar. We have to square the first term, 4a squared, the second term, 3b, 9b squared, to form the first and the third or the last term in such an expansion. To form the middle term, we only need to look at the sign here. It remains the same if it's a plus, and we multiply the two terms together. That's 2a times 3b gives us 6ab, and we have to double that to form 12b, because of the fact that it's repeated always, as we saw in the grid for such a type of expansion. And in the case, of course, of the negative, it's exactly the same expansion. The terms are the same except for the sign of the middle term, which will be the same as the sign of this particular binomial, which must be squared. We can see exactly the same in problem or example number 3 in this case. If we are given 3a squared plus or minus 4b to the power cube, if we square all of this, according to our square of a binomial structure, we have to square the first term, which is 9a to the power 4, square the second term of the binomial in the bracket, which is 16b to the power 6, just check that, applying our exponent rules. And then for the middle term, we have to multiply the terms together, that is 12a squared b to the power 3, and then double that, so it becomes 24. Remember, the sign of the middle term remains the same as the sign of the binomial to be expanded or to be squared in this particular instance. Let's look at the fourth example. Here we have the square of a binomial, an expression with two terms here, and in front we have a minus 4 as a numerical coefficient in addition. So we first square, and whenever you find the term of such an expansion, you must remember to at all times also multiply with minus 4 to get the resultant term of the expansion as indicated. So let's see how this works. Remember, we have to square the first term, which is 9x squared y squared. Okay, and then we still have to multiply by minus 4, and that gives us the minus 36x squared y squared as the first term of this expansion. We have to square the second term as well. Gives us 25z to the power 4. 25 must still be multiplied by minus 4, so it gives us minus 100z to the power 4. And finally, we can just multiply these two terms together for the square of such a binomial. So we get minus 15 x times y times z squared, and that must be multiplied by minus 4 still. Okay, so in this case we have minus 15. Remember, there are two of them, always double that, gives us minus 30, and then multiply with minus 4 still gives us plus 120, as we expected for the middle term of such an expansion. Finally, we look at this particular case. We can also have a case where we square a trinomial, that is, three terms in the bracket, trinomial, to be squared. In other words, you multiply the trinomial with itself again. How do we handle such a case? Well, we may decide to see the first two terms as one unit in brackets, indicated in the round brackets as we see on the screen, and then use a different type of bracket maybe to indicate, and then we have the same structure as we have for the square of a binomial. This is the one term, and that's the second term, and if we apply that, we see we have to square the first term as we did before, and we also have to square the second term finally, which is 16b squared, the last term. And then we can multiply, of course, this particular term, as we call it, if we have the bracket in such a case, multiply that 3x minus 2y with the second term 4b. And this is what happened here. We multiply the 3x minus 2y, okay, with the other term 4b, and remember that gets repeated twice because of the structure we saw from our grid. So you have to multiply by 2 again. That's why we have here 8 times and then b. Okay, that's 2 times 4b times the term 3x minus 2y, as we see this as one term. And then of course it just means that afterwards we have to multiply this out, 8b into 3x minus 2y, to form the terms as we have it here. Okay, and we have to expand this as we normally did with the examples 1 to 4. And then we have the expansion, if you list all the terms in this case, which will then form the square of this trinomial. You can check this step by step and apply the techniques that we have seen earlier and see if you agree that you get these particular terms if you have this particular expansion known as the square of the trinomial in this particular case. The second very important special product that we'll consider is the difference between two squares. Now in such a case we have the product of two binomials where the only difference between the two binomials is the sign between the terms, as you can see. In such a case the expansion is much simpler than before. It is only the difference between the square of the first term and the square of the second term in each of those binomials. Now where does this come from? Let's apply our grid method that we saw before, and let's list the first binomial, the terms a and b, in the first row as before, and a and minus b in the first column for the second binomial of this product. If we now compute the products, in other words complete the grid, then we see we have a squared minus b times b gives us minus b squared, and then the similar terms in red will be in one case plus ab, a times b, and in the second case minus b times a, which gives us minus ab, and these two terms will cancel if we add them together. It's similar terms. So therefore we do not have a middle term in such an expansion, and the result will be a squared minus b squared as indicated. Let's have a look at a number of examples where we apply the difference between two squares as an expansion of a product of this type. In the first case, we have to multiply 5a plus 7b with the second binomial 5a minus 7b. Only the signs differ in this case. Immediately we can write down the square of the first term, 25a squared, and the square of the second term, 7b all squared, gives us 49b squared, and then we put a negative in between, as we've seen from our general case that we considered before. So the answer is then 25a squared minus 49b squared, and the middle terms will cancel. That is then the difference between two squares as an expansion of such a product. Second example, similarly, we have the difference between two squares, type product here. Because of the structure of the two binomials, they only differ in the sign, but now we have a numerical coefficient in front, minus 4. And remember, we apply the rule for the difference between two squares for the expansion, and then we still have to multiply with minus 4 in each case. So in the first instance, we have 2a squared all squared, which gives us the 4a to the power 4. If we multiply that with minus 4, we get minus 16a to the power 4. And similarly for the second term, we square it first of all to get 25b to the power 6. Put a negative in front because of the difference of square type expansion in this case, and then multiply by minus 4 finally to get 100b to the power 6 for this expansion. In example 3, we have a similar situation. In this case, however, we have the binomials 3ab minus 5cd, and in the second case 5cd plus 3ab. So the order is not correct, but since we have the commutative law for addition, we can swap the order for the second binomial in this particular product and rewrite it as 3ab plus 5cd. Now we can see the structure is clear. We have two binomials and only the sign differ between the two terms in each case, and we can apply the difference between two squares type expansion. And we have the result, as you can see on the screen. You should be able to check this. Finally, we can have more complicated cases where the difference between two squares will help us to expand a product. For instance, we may have the product of two polynomials in this case, each with 4 terms, can you see? And in this case, if we rearrange the structure of this particular product in the way that is suggested by the next line, what did we do? We considered a plus b to be one term. We put a bracket around it in both cases, and then we realize or recognize that 2m minus 3n, if we put a bracket around that to make it a singular term to be considered for the expansion, we notice that on the other side, for the second factor, if we take the minus as a common factor out, then we see we have identically the same unit, 2m minus 3n, which is a binomial of course on its own, but we treat it as a singular term. And then we have only a sign difference between the two expressions, and that really fits the difference between two square structure, and we can apply the same technique as before. In other words, take the square of the first unit or the first term as it is treated in this case, a plus b all squared, minus the second term 2m minus 3n all squared for the difference between two squares expansion of this particular product. And after that it should become easier then, because this square is exactly what we have treated before as just the product of two binomials to be expanded and have the 3 terms as indicated. That should be familiar to you now. And we do the same with the second bracket, the square, just the expansion, becomes the 3 terms as indicated. But remember, there's a negative in front, so be careful. You have to multiply the negative in with all 3 terms to have exactly the expression as we see it on the screen. So this is a slightly more complicated example, but it shows you that the difference between two squares can be applied in more than one way to simplify the expansion of a product which is seemingly complicated, like we have in example number 4. To conclude this lesson, let's have a look at the third very important special product called the sum or difference between two cubes. In such a case, we have a product of a binomial and a trinomial, 2 terms, 3 terms, as indicated on the screen, with a special structure. And in this particular case, it will result in a very simple expansion, where instead of having 6 terms, remember if you multiply each term on the left with each one of the 3 terms on the right for this product, then we normally get 6 terms, but in this case 4 of them will disappear through simplification, cancellation, and we're left with only the 2 terms as indicated, the sum of 2 cubes in this case. Why will that be? Well, that is because we have some of the terms that will cancel if we add similar terms in the expansion together, and we'll demonstrate that using the grid method in a moment. So either we have this structure, and you can see the structure here, x plus y multiplied y, the first term must be the square of the first term here, and the last term in the second factor must be the square of the second term in the first factor, and with the plus here we need a negative, and then just the product of the terms of the left hand side polynomial, in this case a binomial. If that is a structure, then we always have this type of expansion, which is very simple, lots of cancellation and simplification in that process. This, or we can have the x minus y, where the plus is replaced by a minus, and the right hand side factor in that case must be a plus instead of a negative. And then we have a difference between the cubes. So the sum or the difference between cubes will be the result of the expansion of products of this particular type. Now, where does this come from? Let's just have a look at the grid method as we considered it before. The left hand side factor or the binomial, let's list the terms x and y as the first row, and let's just take care of the plus and the minus. In this case it's plus or minus y, and in the first column let's list the terms of the second factor of this product. In other words, x squared, either minus or plus. Note the order is different here. xy for the second term, and then of course the third term y squared in both cases. If we now complete the grid by multiplying all possible products that will be necessary for the terms of such an expansion, we see that we generate similar terms in red and similar terms in blue, apart from the x to the power 3 and plus or minus y to the power 3 that we get when we multiply x squared with x and y squared with either plus or minus y in this particular instance. Also notice that the signs of the two blue similar terms will be opposite, and so will the signs of the similar red terms be opposite. So if we add them together, similar terms should be added together. To simplify, we see that we have cancellation, and therefore we're only left with the two terms as indicated, which gives us the sum or the difference between the two cubes. For example, if we multiply minus or plus xy with, in this case, plus or minus y, then in both cases we get the answer minus xy squared. Whereas if we multiply, for example, the y squared with the x in both cases, here we have plus xy squared. So therefore those two will cancel. And you can check the rest of those terms yourself. Let's have a look at a few examples where we capitalize on the structure for the sum or difference between two cubes as the expansion of a product. Let's have a look at this product. Here we have a binomial multiplied with a trinomial, but more than that, we notice that the first term is the square of 2x, the first term of the binomial on the left, and furthermore the third or last term for the trinomial on the right hand side, 1, is the square of the second term of the binomial on the left hand side. So that fits the structure for the sum or difference between two cubes, because you see that this middle term over here is in fact the negative of the product of these two terms, and that really is what we need from our structure up there. So we can immediately apply the formula for the difference between two cubes and write the expansion as 8x cubed minus 1. In example 2 we have a similar situation, but in this case we have a plus with the binomial, and the middle term for the trinomial has a negative. And we also notice that the first term on the right is just the square of the first term on the left. The final or third term on the right hand side factor is the square of the second term from the left hand side factor. We have the middle term here is just the product of the two terms with a negative, and immediately we may apply then the formula for the sum of the sum between two cubes in this case, and we have the structure of the answer then, the expansion, immediately 2x squared all cubed plus and then 3 all cubed, which if we simplify we get 8 times x to the power 6 plus 27. Finally, in the third example we have a product which is seemingly more complicated, but it has exactly the same structure as what we saw in the second example. We notice that the first term on the right hand side for the factor is the square of the first term on the left hand side for this factor. Also the final or third term on the right is the square of the second term, and we have the product of the two terms here, 15xym with a negative. In this case, 15xym squared with a negative, which obviously fit the structure of the sum between two cubes expansion, and we can immediately write down the answer as the cube of the first term plus the cube of the second term, simplify, and we have this particular expansion as the final answer to the product in this particular case. I think the time has arrived now for you to try some of the special products that we have discussed in tutorial 5. Here we have a number of problems, 6 of them, where you have to expand using the techniques that were discussed in the previous slides. So at this point in time I suggest that you pause the video, do tutorial 5, and then come back and view the solutions. Let us briefly have a look at the suggested solutions for tutorial 5. In the first problem we had to multiply the binomial 3a minus 2b with itself, so it's just the square of the binomial expansion in this case. So if you can remember, we square the first term, 9a squared, and the second term, 4b squared, and the middle term in such an expansion will be twice the product of the inner terms. In this case, minus 2 times 3 is minus 6ba, double that, we have minus 12ab, and that will be the expansion of this particular product. In problem 2 we have a similar situation, but in this case we have the square of the binomial 2x squared plus 3y. In the same way we square the first term and the second term of the first binomial, and this becomes the first and the last term of the expansion, and twice the product of the inner terms in this case will be the middle term, which is 6yx squared times 2, which makes it 12x squared y, if you would like to write it that way. So straightforward application of the square of a binomial formula that we considered before. In the third instance we see that we have the product of the binomial 5a squared minus 7b with another binomial which is very similar, it's just a change in sign. So if there's only a sign change between the two terms in such a product, then clearly it gives us the formula of the difference between two squares, and we have to take the square of the first term, square of the second term, and just put a negative in between. The middle terms will then cancel as we discussed earlier. So in this case we have 25a to the power 4 minus 49b squared, the difference between two squares formula apply in this case. In problem 4 we can immediately see the structure for the difference between two squares. This really means that if we expand, we only have to square the first term and the second term from any one of the polynomials and write a negative between the two terms. So here we have 9x to the power 4 minus 25y to the power 6 as the expansion of this product according to the difference between two squares formula. In problem 5 we clearly recognize here in the difference between two cubes formula for the expansion. Why is that? The first term on the right hand side factor is the square of the first term on the left, and the final and third term on the right hand side factor will be the square of the second term on the left. And furthermore, if you multiply the two terms together from the left-hand side factor, we get, in this case, the negative of what we expect, in this case 21pqr. Fits exactly the structure of the difference between two cubes, and we expand this product by just writing the cube of the first term on the left minus, in this case, because it's the same sign as what we have for the left-hand side factor, for the expansion, the second term, and we cube the second term without the negative, of course, the 7r all cubed, and just check, this gives us 343r to the power 3, or r cubed. Finally, in problem 6 we have a similar situation where this really fits the sum of two cubes for the expanded format of this particular product. So let's have a look. The first term on the right hand side is the square of the first term on the left. 36 over x squared is just the square of 6 over x. And similarly, the term on the right, the final term, the third term, is the square of the second term on the left, 5x. And furthermore, if we multiply these two terms together on the left, we just get 30. And we have the negative of that. So the signs change or differ here, as we need for the formula for the sum of two cubes. And we apply it by just cubing the 6 over x and also cubing the 5x to have the answer, in this case 16, or 216 rather, divided by x cubed plus 125x cubed. That then gives us the solutions for tutorial 5. In lesson 3 of this video, we will review a very important part of basic algebra, and that is called factorization. So we look at different techniques of factorization, which plays a very important role in general in solving equations amongst other things. To start off, let's have a look at the outcomes for this lesson. In this lesson, we consider the following methods of factorization. First of all, the common factor. This is just a revision from previous schoolwork that you should have done. Secondly, we look at the difference between two squares as a factorization technique. This is also revision. Thirdly, we look at factorization using trinomials. In particular, we look at the perfect square. And finally, we look at the grouping as a method of factorization. Before we consider the different types of factorization, let us first have a look at the question, what is factorization? Now recall earlier, during this video presentation, we considered various special products and expansions of such products. Now, factorization and product expansion are reverse processes of each other. Let me explain. Remember, if we have a product expansion of the type that we saw before, let's say we multiply together two binomials, then we have various techniques, one of them being the application of the FOIL rule, which means we first multiply the first terms of the factors together to get the first term of the expansion. Then we multiply the outer terms of this particular product to get the second term of the expansion. After that, the inner terms to get the third term of the expansion. And finally, the last terms of the two factors of this product to get the final term of this particular expansion. Now this process in reverse would just be the factorization of a particular given expression. So here we are. If we factorize an expression of this type, that is writing the sum of terms, 4 terms in this case, as a product of two expressions, two binomials in this case. So in other words, we're taking a sum of terms and write it as one single term which consists of a product of factors. That's where the term factorize comes from. We change an expression which normally is in the form of a sum of a number of terms into one single term where we have different factors. In this case, we can see the factors will be a plus b and c plus d respectively. So factorization and product expansion are reverse processes of each other. It's much more difficult, obviously, to factorize an expression than it is to expand an expression. So let's look at a different case, another case, the product of the binomial and the trinomial. If we expand, we can write it in a systematic way. We can write it in this format as a sum of terms. That is, if you multiply each term for the left-hand side factor with each term individually for the right-hand side factor. And in this case, we generate, as we expect, 6 different terms in general. They may be the same, there may be simplification, but in general we get 6 terms in such an expansion. Now the reverse process, if we have started with this particular expression, the sum of the 6 terms, then writing it in this format as a single term, product of 2 factors, that is, a binomial and a trinomial, that process is called factorization. The most basic process of factorization is referred to as taking the common factor or factors. Now in such a case, one normally has an expression with more than one term where a common factor or factors occur in each of those terms. And what is more, in this process we must always ensure that the common factor to be taken must be the highest common factor, also referred to as the HCF. Let us explain this by using a number of examples. First of all, let's say we're given this particular expression consisting of 3 terms. Clearly, if we consider each term individually, we see that A, that is the factor A, appears in all 3 terms and also is in this case the highest common factor. If you remove the A as a common factor, this process is referred to as taking the common factor A out, we're left with a bracket, which means we have changed this expression consisting of 3 terms into an expression with a single term which consists of the product of 2 factors, A being one of those factors. In fact, A in this case is the highest common factor. Did you notice that this whole process, referred to as taking the common factor, is in fact the reverse process if one thinks of the distributive law that was discussed earlier? If we apply the distributive law in this case, it means that A must be multiplied into this bracket with each term inside, and then we get back our original expression. So the distributive, applying the distributive rule, is just expanding a product of this kind where we have the product of 2 factors, and taking the common factor or factorization using the common factor in fact is the reverse process. Let's have a look at the second example. Here we only have 2 terms in the expression, but we do notice that in this case 3a squared times x is the highest common factor. In other words, this particular factor occurs with each one of the terms. It's actually built into the 9a to the power 3x squared, and it's also built into this particular, it's part of the second term, 6a squared xy. And if you remove that highest common factor from this expression by taking it as a common factor, then we may write this expression consisting of 2 terms as the product of 2 factors where one of them is the highest common factor, 3a squared x. And remember, if we now apply the distributive law to check, if you multiply in, you must get back exactly the terms that we started out with. Have a look, 3a squared x times 3ax gives us 9a to the power 3x squared. Check that. Just apply your exponent rules in this case. And also if you multiply 3a squared x with minus 2y, we again get the second term that we had before. A third example. Here we have to consider the expression as a whole and find the highest common factor. Now clearly we can see that 2 the number 2 is common to the first term and to the second term, so that's part of the highest common factor. But if we apply preliminary algebraic manipulation in some cases, we can actually find the highest common factor, which is slightly different. Have a look at this. We notice that if we multiply this particular expression y minus x in the bracket by minus 1, it becomes exactly the same as the expression in the brackets for the first term. So then those two factors will be common as well. So if we multiply each side with minus 1, clearly we have to compensate by multiplying by minus 1 outside as well. So we change the minus 4 to a plus 4 by multiplying by minus outside, do the same inside, and suddenly we have another common factor, another part of my highest common factor, which can then be taken using the factorization process that we're discussing. So the highest common factor now is 2 times, in brackets, x minus y. And if we take this as a common factor from both these two terms that we started out with, then clearly we have our final factorized version of our original expression. The original expression had 2 terms. The final factorized version of that obviously have only a product, in this case, of 3 factors, 2 times x minus y times x plus 2y. Now that then demonstrates the use of the technique common factor taken from a given expression. Let us consider the second technique for factorization, namely grouping. In this case, we apply the technique when there are more than 3 terms to be factorized, normally 4, in an expression. And the terms are grouped together in pairs, normally, in order to apply well-known factorization methods. The only one that we know of at this stage will be the common factor method. We will also discuss other methods later on in this video. So let's have an example which demonstrates in a classical way how grouping, the factorization technique called grouping, can be applied in the case where we have 4 terms that we start out with. Here we have the expression with 4 terms. We have 2 choices here. We can either group the first 2 terms together and term number 3 and 4, or we can group term number 1 and 3 together and also term number 2 and 4 to apply the factorization called grouping in such a case. Now, in the first instance, if we look at this particular expression, if we look at the ratio of the numerical coefficient of term 1 and term 2, and we simplify that, we get a ratio of 2 to minus 3. That's dividing through by 5 on both sides. If we look at the numerical coefficients of terms 3 and 4, and we divide through by minus 2, and we compare the coefficients, we see that the ratio is minus 4 to 6. If we divide through by minus 2, it's also 2 to minus 3. So the same numeric ratio between the numerical coefficients of the pairs of terms that we have chosen. That actually tells us that in this case we can apply the grouping technique successfully to factorize this particular expression. Similarly, if we look at the second possibility where we group the term number 1 and 3 together and term number 2 and 4, we also see that the ratio 10 to minus 4 in the first instance is the same as the ratio of minus 15 to 6, which is of course linked to the second choice there for a pair, term number 2 and 4 together. If we reduce it in both cases, we see that in fact it is equivalent to the ratio 5 to minus 2, apart from a negative. So in both cases we can apply the grouping technique, and in the first instance, if you have this choice, we have the following. Taking the 5x squared as a common factor for the first 2 terms, we're left with, in the first instance, 2x cubed. In the second instance, we're left with minus 3. and taking the common factor from terms 3 and 4, in this case, that is minus 2, we're left with 2x cubed minus 3 as well. So you see, you create a second common factor in the two terms by taking the common factor from the pairs independently as it was chosen to start out with. Having this particular expression in the brackets, the round brackets, as a common factor, and apply the common factorization technique again, the second time around we take this as a common factor and we're left with 5x squared minus 2, which in fact show the factorized version of the original expression using the grouping technique. In the second case, when we group terms 1 and 3 and 2 and 4 together respectively, we have a similar situation. Taking the common factor now of term 1 and 3, that is 2x to the power 3 again, we're left with 5x squared minus 2, just check that, from term 1 and term 3, and taking the common factor from term 2 and term 6, that is minus 3 in this case, we're left with 5x squared minus 2 again. We create a common factor which can be factorized using our particular skill that we have seen earlier on, the common factorization process, and in the end it gives us exactly the same expression as before. The common factor 5x squared minus 2 and then multiplied by, in brackets, 2x cubed minus 3, which is the second factor of the factorization. So the result is exactly the same, whether you actually group terms 1 and 2 together and then also 3 and 4, or whether you start with terms 1 and 3 as a grouping and term 2 and 4 together as a grouping. This technique gives us exactly the same result. I think you should be ready now to try a fairly comprehensive tutorial on the common factor and grouping techniques of factorization. This will be then tutorial number 6. So I would like you to factorize the following expressions. We have 8 of them, so you should take some time, put some time aside to try this particular exercise, and the two techniques, common factorization and grouping, must be aimed for. At this point in time, I suggest that you pause the video, do this tutorial, and then come back and view the solutions. Let us briefly look at the suggested solutions for tutorial 6. In the first problem, we had to find the greatest common factor and factorize the expression as it is given, 3 terms, and in this case, if you look carefully, the greatest common factor will be 3 times a squared times b times c. Taking that from each term, we remain with, and you put the brackets for the second factor, 2ab minus 5c minus 6bc. Just check that. You clearly have to utilize your exponent rule for multiplication here in order to check the answer as well, because if you multiply out the 3a squared bc into this bracket using the distributive property, you should get back exactly the terms of the original expression. In the second problem, we have a similar situation, except that it's not immediately clear what the common factor must be. Only if we multiply the second term by a negative 1 will we create a common factor, namely a minus c. Change the sign inside this bracket, so you have to put a minus outside. And in that situation, it is clear if we take the common factor a minus c, we're left with the terms q minus m, which will then form the second factor for this particular factorization. In the third problem, we're given an expression where it's clear what the common factor is. In this case, at least part of it, the a plus b is common. But we also have the x as common to both of those terms. So the common factor, that is the greatest common factor, will be x times a plus b. And if we take this as a unit from the terms, we're left with, in the first instance, x. And in the second term, if we take the common factor, we're left with y. So the factorized format of this particular expression will be then x times a plus b times, in brackets, x plus y. Let's have a look at problem number 4. Here we're given the expression, it's a numerical expression, 19 squared times 7 plus 19 times 7 squared. Now the same rules apply as before in terms of exponents, so what is common to both of these terms will be the term or the expression 19 times 7. If we take this away from the first particular term, multiplicatively that is, then we're left with 19. And if we take 19 times 7 away from the second term, then we're left with 7. So this is then the factorized version of this particular expression, where we have utilized the common factor as a technique for factorization. In problem number 5, we're given 4 terms, and that is already an indication that we're looking towards grouping, utilizing the grouping technique for factorization in this case. And we note that the ratio of the numerical coefficient of the first and the second term will be 8 to minus 6. And if we divide that by 2, it will be 4 to minus 3, which is the same as the ratio if you look at the terms 3 and 4 together as a pair. Look at the numerical coefficients, 12 and minus 9. And if we divide through here by 3, we get 4 to minus 3 as well as before. So this really means that there is a chance of the factorization, grouping factorization, being successful in this case, particularly as we can also see that the first 2 terms have a common factor A, and we're left with factor C and D with the 2 terms, and with terms 3 and 4 we have a common factor B, and we're also left with the factor C and D, particularly for those 2 terms. So if we now have a look at the common factor for the first 2 terms, which will be 2A, take this away from terms 1 and 3, then we're left with 4C minus 3D. And similarly, if you look at the common factor of terms 3 and 4, which is 3B, check that, we take that away from terms 3 and 4, we're left with 4C minus 3D as well. So we create a second common factor, which if we take this out, we're left with 2A and 3B respectively, which is the second factor of this particular factorized version of this particular expression. So this is how we apply the grouping technique then. Another example of its application. In problem 6, we again given 4 terms, and in this case we notice that if we take the common factor from terms 1 and 2, that's A squared, we're left with a factor 7A plus 5, and this is exactly what we have for the remainder of this expression, 7A plus 5, and we can write it in this format if you wish. Just take 1, the number 1, value 1 from each of these terms if you want to take a common factor, because that's the biggest common factor for those 2 terms, plus 1. Then we can see we have a common factor now, which we can take, and the remainder from the 2 terms that we have now will be A squared plus 1, and that becomes the second factor of the product, which is then the factorized version of our original expression. Let's have a look at problem number 7, which is very similar. Again, an example of the application of the grouping technique for factorization. In this case, we consider terms 1 and 2 again as a pair, and also 3 and 4. We take the greatest common factor for the first 2 terms. In this case it's 6y, and we're left with 3y plus 2 if you apply the common factorization to the first 2 terms exclusively. Do the same with terms 3 and 4. The greatest common factor in this case will be minus 10a. Look, the a is common, as well as the minus 10. And if we do the factorization, the common factorization for terms 3 and 4, we're left with the second factor 3y plus 2, which is again common. And we apply the common factorization once more. And then we're left finally with the factor 3y plus 2. Okay, and what remains after that will be in our case 6y minus 10a, but there is a common factor 2 in that case, so we write that separately. So 2 times, in this case, 3y plus 2 multiplied by 3y minus 5a will then be the final factorized version of this particular original expression using the grouping technique. Finally, if we look at problem number 8, we have an expression which consists seemingly of 3 terms, but in such a case we first expand the middle term by multiplying from the right by x into 3a plus 2b to get this particular expression with 4 terms, where we can then apply the grouping factorization technique. In this instance, we group terms 1 and 3 together, and also terms 2 and 4 indicated in red on the screen. So from terms 1 and 3, the common factor will be x, and we remain with x plus 2b, whereas from terms 2 and 4, the greatest common factor will be 3a, and we left also with a common term then, a common factor rather, x plus 2b. So this common factor x plus 2b from the 2 terms now must be taken, and we left with the terms x in the first instance and also 3a in the second case. So the factorized version of the expression given in problem number 8 will be x plus 2b in brackets multiplied with x plus 3a in brackets. So this gives us then the suggested solutions for tutorial number 6. The third important technique of factorization that we will discuss is called the difference between two squares. Now we have seen this already, but in a different format. Normally the expression that can be factorized using this technique consists of 2 terms only, and the terms will be separated by a minus, and both terms will be perfect squares. So here we have the expression really that we have to then factorize to be the product of 2 factors in this format. Now you recognize this as really what we have seen before as a special product, where we multiplied 2 binomials together, where the binomials are, apart from the signs, exactly the same. So whenever we start with an expression which can be viewed as a perfect square minus another perfect square, one can always write this expression in factorized form using this particular structure, which is just the reverse of the process that we have seen before when we expanded the special product of 2 binomials of a specific type as indicated. Let's have a look at a few examples of where we apply this technique to factorize. First of all, this expression consisting of 2 terms with a negative in between, and both these terms, the first one as well as apart from the negative the second term, can be viewed as perfect squares. Notice that 4a squared is just 2a all squared, perfect square, and 9b squared can be viewed as 3b in brackets all squared. So it's in fact the difference between 2 squares. Now then it gives us immediately a way to factorize this, to write it as a product of 2 factors, where in fact the square root of the first term and the square root in this case of 9b squared will be the terms that will be utilized in the brackets as indicated, first with a plus and then with a negative, and that gives us the factorization of this expression using the difference between 2 squares. Just remember, we can use the FOIL rule as well to check our answer, and if we expand this according to the techniques that were discussed earlier in this video, we see that the inner term and the outer terms will cancel as indicated as part of the FOIL rule application. Okay, if we multiply the first terms together, we get again 4a squared, and if we multiply the last terms together, we again get minus 9b squared. The middle terms will cancel as can be seen according to the FOIL rule. Some of these terms are similar that we generate, and we ended up only with the 2 terms if we do this in reverse. The second problem, we given these 2 particular terms, the difference of 2 terms there, and both of them can be considered, apart from the negative, as perfect squares. Notice that the square root of the first term is 3x divided by 4, and if you look at the second term, y to the power 4 over 25, the square root of that will be y squared divided by 5. Of course, we just treat the negative separately in such a case. Now clearly, applying the rule directly, we have this particular factorization according to the difference between two squares formula. Remember, the one case we have a bracket with a plus, and the other case a bracket with a negative. Apart from that, the two brackets will be identical. The terms in the two brackets will be identical. Let's have a look at the third example. Here, of course, we have again the difference between two squares, because x to the power 4 is just x squared all squared. And similarly, y to the power 4 will be y squared all squared. Applying our technique here, we have the terms x squared and y squared, first with the plus and then with the negative, and we multiply the two brackets together. And you can check again using the FOIL rule if you want to recover your original expression if you should expand this product. But remember, the aim here is to write the expression in factorized form, which means only one term, only factors. Here we have two terms. In other words, we're changing an expression consisting of two terms to a single term consisting of two factors, represented by the brackets in most cases. Okay. In this case, however, we can actually continue, because we see we immediately generate the second factor of the factorization is again the difference between two squares. So if you really would like to simplify this particular expression through factorization further, we need to apply the difference between two squares technique once more. And that gives us then the final factorized version of our original expression consisting of two terms, namely x squared plus y squared in brackets multiplied with, and then x plus y, x minus y. If we take this part, expand it separately, of course we will get back x squared minus y squared again. In the fourth example, we have this particular expression. Clearly again, we have x minus 2 as a factor in one case and 2 minus x. Now whenever that happens, we know that we can swap this particular terms within this particular bracket by putting a negative in front, and that is exactly what we do. And in this case, we see we have a common factor. So you see we're combining a common factor with the difference between two squares in this particular problem. So it's like two steps in the same problem. Taking the common factor x minus 2 in this case will result in the expression x minus 2 common factor multiplied with, in the first instance we have 4x squared left, and in the second term here, if we take x minus 2 away, we have minus y squared. Now this particular factor of this product we recognize as a difference between two squares again. So we apply the difference of two squares technique right there to get the final expression, which is x minus 2, and in this case this becomes 2x plus y multiplied with 2x minus y. And you should know why. The square root of the first term is 2x, the second y squared, the square root is y, and we have the sum and the difference as the expansion here, or not the expansion, as the factorization using the difference between two squares technique. Now there you have a couple of examples which illustrates this particular method of factorization, and also sometimes combining that with the common factor technique for factorization. In tutorial 7, we would like you to consider a number of problems linked to the difference between two squares technique of factorization, combined maybe with some of the other techniques that we have discussed. So I would like you to factorize the following expressions. Here we have 9 problems. It's quite a comprehensive exercise. So I suggest that you pause the video at this stage, do tutorial 7, and then come back and view possible solutions. Let us have a look at the suggested solutions for tutorial 7. In the first problem, we were given an expression which is already given in the format the difference between two squares, and we can immediately write this according to the formula as 17 plus 16 times 17 minus 16. And that is where you can stop. The question was to factorize this particular expression. In the second problem, we're given a similarly simple format, 4a squared minus 9. If we view this expression, the first term of this expression, 4a squared, is just 2a all squared. We can immediately go and write this in factorized form. That is, if you see 9 as 3 squared, and the format will be 2a plus 3 times 2a minus 3 in this case. Problem number 3 is also straightforward. If you can find the square root of the first term and also the square root of 9b to the power 6, then you can just apply the method of the difference of squares factorization to write the answer as 5a squared over 4 plus 3b cubed in the one instance, and just the same expression in another bracket with a negative instead of a plus. Problem 4, here we have to find the common factor. In this case, you see that the two terms given has a common factor of 5xy to the power 4. And this is important to notice. Whenever there's a common factor in the given expression, we first apply the common factorization technique, and after that we see for the other factor if we can apply any other form of factorization to it. In this case, taking 5xy to the power 4 is the common factor. We're left with the second factor, 4 minus 9x squared y squared, which of course is the difference between two squares. That is, if you see 4 as 2 squared, and if you see 9x squared y squared is 9xy all squared. Applying our formula for the difference of squares, factorization, we have the following expression then finally in factorized form. 5xy squared times in brackets 2 plus 3y, and then also in brackets 2 minus 3xy in this case. In problem number 5, we're given a bracket squared, so you view this as a unit, minus 9c squared. Now clearly one can view this as the difference between two squares, and you treat the expression a plus b as a unit in this case, or as a single term. And if we rewrite this using the difference between squares factorization structure, then we have a plus b plus 3c, which is the square root of 9c squared in the one instance, using maybe a different type of bracket, multiplied with a plus b again, but then the negative 3c instead of plus 3c. What one can do now is to just remove the bracket inside, the round bracket inside the second factor, and the same in the first bracket here, the first factor, and write this expression in factorized form just as we have it on the screen. In problem number 6, we're also given a difference between two terms, and clearly each term can be viewed as a perfect square. The first one is 9 times whatever we have in brackets here, x squared minus y squared is a unit, to the power 2. So 9 times this, everything to the power 2 or squared. And the second term in this case, we can view the 16 times c minus d all squared as just 4 in brackets c minus d everything squared. So the difference between two squares is also in order here. And if we write this out, we keep the expressions in round brackets as units within this particular bracket, the first factor of the factorized format. So we have 9 times in brackets x squared minus y squared as the first term inside of this particular first factor bracket, and 4 times c minus d as the second term inside the first factor bracket. And then again you repeat this, but you put a negative instead of a positive. This is according to the difference of square in our factorization method. Okay, what we have now inside here, we can actually multiply out using the distributive property and rewrite everything without the brackets inside of the factors as we have it in this particular factorization. You do the same for the second factor, just multiply in the 9 and the minus 4, and we rewrite this everything in factorized form with only two brackets, two factors in this case, as indicated on the screen. In problem number 7, we are given the following expression, 2 times in brackets a plus b all squared minus 18. Immediately we see there's a common factor for the two terms given. So we take out the common factor, and if we do that, then clearly what remains is a plus b all squared minus 9, which can be viewed as the difference between two squares. And if we apply the technique, we have 2 times in brackets then a plus b plus 3, and then a plus b minus 3. Remember, the a plus b is just from the bracket in both cases, the first term from this difference of two squares in this case. In problem 8, we're given the expression a to the power 8 minus b to the power 8. Now this can be viewed as the difference between two squares. Why is that? From our exponential rules, we see that a to the power 8 can be viewed as a to the power 4 all squared. And the same with b to the power 8. That becomes b to the power 4 all squared. So we have a difference between two squares, where a to the power 4 and b to the power 4 is at play. And we can see this exactly here. If we apply the difference of squares factorization method in this case, we have this particular product of two factors, a to the power 4 plus b to the power 4 multiplied with a to the power 4 minus b to the power 4. Now clearly this is again a difference between two squares, that is a squared all squared minus b squared all squared. And if we apply our difference of squares factorization once more, we can expand this particular bracket to become the product of two factors as indicated. And finally, once more, this again is a difference between two squares. So finally we can write the original expression consisting of two terms, difference between a to the power 8 and b to the power 8, as one single term where we have four factors as indicated. Finally, if we look at the problem number 9, we have in this case the expression. It seems that the expression consists of three terms, but if we view carefully the first two terms together and view this as a difference between two squares, we have had a similar problem before, then we can rewrite this in factorized form as 2a plus 3b multiplied by 2a minus 3b in the normal way, and then suddenly we see that we have a common factor with the second term. So we have two terms now, but 2a minus 3b is common. Immediately we apply the common factorization method, and we take out 2a minus 3b as a common factor, and we're left with 2a plus 3b in the first case, and in the second case also with a negative obviously between, we have the expression 2a minus 3b. Consolidating what we have inside here, see the 2a and the minus 2a will cancel, and in this case the 3b and minus 3b becomes 6b. We can finally write this in factorized form as 6b multiplied with 2a minus 3b. So can you see sometimes different techniques of factorization can be combined together with, in the end, simplification to write an expression consisting of more than one term as a product of one or more factors. We will now consider factorization of trinomials. This type of factorization is indeed very important and will frequently be encountered as part of the NCS syllabus. What is important for this type of factorization? First of all, the framework. Secondly, the factor combination that is chosen. In particular, the placement of the selected factor combination is very important. Let us have a look what I mean by framework in this sense. Now, with the factorization of trinomials, we have to express a given trinomial as a single term in factorized form. We have the product of two factors in brackets as indicated. Now we have three possibilities in general. The sign between the terms for each of these factors may be both positive, both negative, or have a different sign, and that is important to determine as well. we will demonstrate the utilization of this type of factorization using examples. So let's have a look at these 4 cases of trinomials. In both cases, we have as a start the numerical coefficient 6, and as the last term we either have a plus or a minus 10. Now that will determine to a large extent how we utilize certain factor combinations for the numbers 6 and 10. What do we mean by factor combinations? We always have to look at the possible factorization of the first numerical coefficient of a trinomial and also the final numerical coefficient. So for example, the 6 and the 10, if we consider that, we have factorizations 2 times 3 or 1 times 6 for the first numerical coefficient, and for 10 of course 10 times 1 or 5 times 2. Now combinations of these factorizations of 6 and 10 respectively will determine whether we can successfully factorize this particular trinomial or not. Let's have a look how we go about in deciding which factor combination should be utilized for each case. I notice that if I take 3 times 5, which is 15, and add to that 2 times 2, I get 19, and 19 is exactly the numerical coefficient of the middle term. And this is most important. We look at the numerical coefficient of the middle term and we decide how can I utilize the factor combinations of 6 and 10 to actually make up this particular value, the numerical coefficient of the middle term. Since I have 3 times 5 plus 2 times 2 is 19, I can utilize it and find the correct combination to successfully factorize this particular trinomial. For example, we know that the product of the inner terms and the outer terms added together must give me the middle term in general for such an expansion. We've considered the expansion of such products earlier in this video. So therefore, we know that 3 times 5 plus 2 times 2 is 19 will be the correct combination utilizing the factors of the numbers 6 and 10 in order to generate the correct numerical coefficient for the middle term in this case. Also note that if your third term for the trinomial, that is the square of the unknown term, is positive, then either we have both these factors will have a plus in between the terms, or it may be that both of these signs will be negative, as we'll see with the last example that we will discuss just now. Let's have a look at the second case. Here we have a trinomial again. We have the same first and last numerical coefficients, but we have a different numerical coefficient for the middle term. Again, we utilize the different factorizations of the numbers 6 and 10 and choose the correct factor combination to successfully factorize this particular expression in the way we have seen before. Since we notice that 2 times 5 plus 3 times 6, 10 times 6 is 16, we know that we need 16 for the middle term, and in this case the middle term is negative, and this has a significant effect on the factorization structure as well. So we know then that we have to place the factors in this particular order, this combination. Since the middle term, have a look at this, will be generated by the inner product, minus 2 times 3, which is minus 6 AB, and also added to that 2 times minus 5, which is minus 10 AB. Both negative will give us a negative, in this case, going along with the 16 to make up the correct middle term for this type of factorization. So very important then to look for the factor combination of the numerical coefficients of the first and the last terms of such a trinomial in order to factorize effectively. Also note here that if this is a negative in the middle term, we have here in this case two negatives for both of those factors as indicated in some cases. Not in all though, only in some cases. For case number 3 here, look at this trinomial. We notice that 6 times 10 minus 1 times 1, which is 60, minus 1 is 59, and we're looking for the 59 to generate as the numerical coefficient of the middle term once we have this factorized form. And let's see, in this case we have a negative for the third term, minus 10, and we put together the factors as follows. Factor combination in this case would be a 1 in this case, and a 1, that is the outer. In this case we have 10 and 6 for the inner. Remember, it's 60 minus 1, so this must be a minus for the second factor between the two terms to generate 59, that is plus 59 for the middle term. And for the rest, of course, 1 times 6 and 10 times minus 1 gives us again the plus 6 and the minus 10. So it comes with practice, but at least we have some structure here and a way of writing down the factors of the numerical coefficients of the first and the last terms, and look at combinations that will actually suit us in order to find the correct middle term, particularly the numerical coefficient of the middle term. Let's have a look at the last example here. In this case we look at the combination 3 times 5, 15, minus 2 times 2 minus 4 is 11. Since we're looking for 11 as the numerical coefficient for the middle term, together with the negative. So the negative has a specific influence in this case. As we can see, we either plus or minus in order to get the correct value for the middle term. That means that if we put together the factors, we will again have a plus and a minus, like we did in example number 3. There are different signs between the terms of the factors in both cases, and here we have also a plus and a minus, and that gets determined by the value or the sign of the middle term as well as by the sign of the final term in such a trinomial. So just check again. If we multiply out here with the middle terms, 2 times 2 is 4, and the outer terms, 3 times minus 5 minus 15, gives us the minus 11. So remember, your middle terms multiply together and the outer terms in combination determines the middle term. So that is why we have to be very careful to select the correct factor combination in order to factorize trinomials in general. So this is then a set of examples which may be very useful as a basis to start factorizing trinomials in general, but it comes with practice, and therefore you should actually aim to do as many as possible of these examples in order to get the hang of it. Finally, we look at the perfect square as a special type of trinomial to be factorized. In this particular case, the first and the last terms of the trinomial will be perfect squares, and the middle term will be twice the product of the square roots of the first and the last terms. Now, if your trinomial has this particular structure, we refer to it as a perfect square in the sense of factorization, and we have then two identical factors in the process of factorizing this particular type of trinomial. Let us have a look at the structure of such a case. Here we have the first and the last terms of the trinomial being perfect squares, and the middle term is either plus or minus twice the product of the square roots of the first and the last terms. And then we have identical factors for the factorization in such a case. Just note the signs will go along with the sign of the middle term in such a case. So in other words, if the second term is negative, we will have identical factors with two negatives between successive terms in each factor. So let's have a look at the examples of this type of factorization of a trinomial, which is called a perfect square. In this case, we see that the first and the last terms of this trinomial are perfect squares. It's 2a all squared, and there we have 3b all squared. Then we also see that the middle term, ab term, will have the numerical coefficient 12, which is twice the product of the square root of 4, which is 2, and the square root of 9, which is 3. So 2 times 6 gives us 12, and this then gives us the structure of this perfect square as we mentioned before, and the factorization is clearly as indicated on the screen. And we have a plus for this particular case for both factors, since we have a positive middle term to start out with. In the second example, we see the first term is 4x squared. Everything squared gives us 16x to the power 4, so that's a perfect square. And here for the last term we have 5y all squared gives us 25y squared, again a perfect square. And the middle term in this case is in fact a term with coefficient 40, which is twice the product of 4 and 5 apart from the sign. So if this is a negative, then we immediately utilize the structure for the perfect square, in this case factorization of a trinomial, and we have this particular structure. Just check that, multiply 4x squared minus 5y with itself, and you can expand and see that you get exactly this particular expression again. That means that your factorization in this case is correct. Tutorial 8 is the final tutorial in this video presentation, and here the focus is on factorization of trinomials. I would like you to do the following factorization problems, 10 of them, each of course linked to factorizing trinomials. At this point in time, I would suggest that you pause the video, do this tutorial exercise, and then come back and view possible solutions. Let us briefly consider the suggested solutions for tutorial 8. Here we have the first trinomial to be factorized, and it is clear that we have the numerical coefficient 1 and 63, factors of which will be 1 times 1, and here we have a number of options. In particular, 9 times 7 gives us 63, and we also know that 9 times 1 plus 1 times 7 gives us 16, the numerical coefficient for the middle term, and therefore this would then be the factor combination which will be utilized to factorize this trinomial. In the second problem we have a similar situation. In this case we have a negative for the second term, and in this case we have both these particular signs between successive terms in the factors will be negative. Do you notice that in this case, if the third term is a positive, the signs will always be the same between the terms in the factors, like in the first problem as well. And just check for yourself, minus 7 minus 10 gives us the minus 17 in this case. That is why we have both of these signs negative in this particular factorization. Problem 3, very similar situation. Here we have, of course, a negative second term and a negative also third term. And the factor combinations again, 7 times 6, 42, obviously. And since this is a negative in front of the third term, we know that the signs will be different from one factor to another between successive terms. It all depends on the actual value or the numerical value of the coefficient for the third term, whether the negative is on the left or the right. That you must figure out by multiplying the inner terms, minus 7, and in this case it will be a plus 6, so to ensure that you get the correct sign for the middle term, namely minus 1 in this case. Problem number 4, very similar situation. Here we have just the factor combination again, 7 and 4, since the numerical coefficient of the first term is plus 1 again, and it's clear what the right combination should be in this case to ensure that we have the coefficient in the middle term, plus 3, 7 times 1 minus 4 times 1 gives us plus 3, and that gives us then the factorization for this trinomial. In problem number 5, note, here we first have to take the common factor 5 before we factorize the trinomial. So always be on the lookout if there's a common factor with each term of the trinomial, that must be taken first before we consider the rest, the second factor, the trinomial, and then factorize it according to the strategy that was discussed. In this case, we see that the structure of the trinomial is a perfect square. Again, if you take 1 and if you take the square root of 9, which is 3, okay, and times 2, we have 6 apart from the sign. So that tells us that this in fact is a perfect square, and we can actually factorize this as x minus 3y all squared, as we discussed before. In exercise number 6, again, we have a straightforward trinomial to consider, and we look at factor combinations of 2 and 15. With 2, of course, since it's a prime number, it's just 2 times 1, or 1 times 2, and we consider 3 times 5, or 5 times 3, as well as 15 times 1, or 1 times 15. Look at the combinations which will ensure the middle term has a numerical coefficient of 13. So here we go, 3 times x and 2x times 5, 10x plus 3x is 13, so this would be the correct combination. In exercise number 7, we have a trinomial which straightforward we can actually factorize using factor combinations of 8 and 21. Just check that this is the correct one, and also note that the middle term is negative, so we have to ensure in this case that we have both negatives between the terms, successive terms with each of these factors of the product, to ensure that we have minus 34 as the numerical coefficient of the middle term. Exercise or problem number 8. Let's have a good look and see. Very similar. In this case, clearly, we deal with a to the power 6. So the middle term will be a to the power 3. Third term in this case is a constant. And it's just a matter of looking at the right factor combinations for the number 4 and the number 15 to ensure that we have the correct middle term in this case. Also note that since the sign of the third term of this trinomial is negative, we will have different signs between our successive terms within each of the factors of this particular factorization. That is to ensure that the final term is negative. Remember, a plus times a minus or a minus times a plus will give us a negative in the third term position. Question number 9, if we can have a look at this quickly again, very importantly, first of all, there's a common factor 2, and we're actually looking at this particular trinomial in the brackets instead of the original one. 2 is already part of the factorization process, or the factorized version of the trinomial that was given. And again, if you look at the factor combinations of 6 and minus 5, in this case, to ensure minus 7 for the middle term as a coefficient, numerical coefficient, we have these two factors. Just check that. And finally, we have this particular problem in number 10, where we have to factorize this trinomial, where we also have an expression in the denominator position. Now in this case, if we multiply, for example, 5 divided by a with 2a, the a's will cancel, and we have a constant middle term that we generate for the product of the outer terms in this case, as well as the inner terms. And we have to ensure, again by the right factor combination, that we have plus 7 in such a case for the middle term. And again, we just have to look at combinations of factors of 5 and 6 to ensure the right combination as indicated on the screen. So this then gives you an overview of the solutions of the exercises linked to tutorial 8, which deals with factorization of trinomials. We have come to the end of this video on basic algebra, that is the part 1 on basic algebra. And remember, consult textbooks for additional examples, as many as possible. Attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in this video. Repeat this procedure until you are confident. Do not forget, practice makes perfect. Goodbye.